Good morning. Today, all I plan to do is make a few little comments on power screws and a few comments on the solutions to problem set 9, which will be posted this afternoon. Then a couple of scheduling things about the final and take any questions you have. This is the time to ask them. First thing I check my notes each time, and I had an error in this stress. This compressive stress is sigma A upon 2. I forgot to divide by 2. So it's still a large stress, okay? That was the point I was trying to make, but there's no excuse for getting it wrong. Okay. And there was a question last time about where I took DC for the collar. So let me reiterate. First of all, the T, and one of you corrected this, is FL, and F was W upon 50, and multiplied by L, you get multiplied by 3, you get 0.059 or 0.06. And this delta T was WFC DC. This is just an approximation, or an estimate, I should say, really. There's no reason for them to keep FC above 0.06, sorry, yes, 0.08, okay, which typically you need to for self-locking. So it could be as low as this. They could make some effort. Then again, it could be as high as F. And here, but here the question was about DC, and let me explain to you why I took roughly the DC apart was the half of the 730 seconds. Well, what's going to happen is in this thing here, the people who designed this very easily spins. Now I've got no load on it, so to speak, but even so, they've tried to make this contact area small. And so if you calculate this contact area, this is a standard calculation. The radius, because the two radii are in the same direction, the radius that goes into this formula is a lot bigger than the radius of either this or this, which would be 4 upon 32, or an eighth. It's 7/8 because they're both the same. So it's been increased significantly by doing this. But even so, when you calculate A, and this is a standard calculation, you get 0.034, okay, very small. And you could take DC upon 2 would be A upon 2. So DC upon 2 is the radius of the contact, and you take it halfway. If you had a uniform distribution, resultant force acts here. Why is that the resultant? Well, you multiply the stress by this area, that's the magnitude, and if you put it halfway through, it'll have the same moment about here. If instead you do that for the, and then the friction force will be perpendicular to that, okay? The resultant for a distribution like this, you can see this is slightly more peaked in the center than out here, and so it has a value of 4 upon pi here, very minor stress concentration. But nonetheless, if you add up these stresses, you can get the resultant force, and its line of action, you then pick it so its moment about here is the same, and you get, not surprisingly, a little bit less than half. Okay? And when you finish with all this, DC would then be 2 times, it'd be about 0.8 times this, and you get 0.289. So my rough estimate was an overestimate. Okay. So then here's the end result then. This is what I was trying to show you. If you work out what delta T is, it's 0.0009 compared to 0.06. So it's about, a 70th of the T, and that's approaching 2 order of magnitude less. At 1 order of magnitude less, it's not unreasonable to leave it out, okay? But you can certainly put it in. At 2 orders, you might as well start forgetting it. And so what happens, these people design these things so these torques are small. Now the book picked a couple of sizable DCs, and so in the calculations there, I don't know that their delta T's were that small. Are there any questions on that? That was done rather quickly. Take you a few minutes to go through that in detail, but the idea is simply that you get, even though you've got this enhanced radius in the contact formula because the two radii go in the same direction, so you have a minus sign when you're adding the reciprocals before you take the reciprocal. And that way you increase the radius because they wrap around. Even so, you get a very small contact, and then about half of that would be the radius of DC, ballpark. And that'll make it small. Whether you have F equals 0.06, or you could have it 0.12, then this thing here would be 0.0011718. Okay, it's still a lot smaller. Okay, it would still be a factor of 30.
How would something like this translate to the exam? Would we be required to calculate that expected DC, or would that be given?
That's a fair question. No, I just wanted to no. If you had to estimate DC, you could sort of look at the outside diameter and just take a factor of 2, just like I did to start with. Okay, but let me answer that question though. In fact, that's going to happen in this problem set. In design in general, you often have to estimate. Okay, you need to you can go on the internet or go look it up in your book to start with, but it may well not be there, and in which case you're going to have to estimate. This is in practice, and so you make your best estimate, and then you try to worst case it. Say, well, what's the worst it could be? Okay. And it may well be that the end result you're looking for is so low a stress that it doesn't really matter whether you're worst case or not. It may be that the difference between your best estimate and the worst case is significant. One of them's got a relatively short life. And so then you say, well, now we need to know this better. Okay. So in practice, what you're doing is making your best estimate, and the internet's a great source for these things. And then making your worst estimate. What's the biggest value I saw? And then what's the biggest it could be? And then you do both calculations and decide, do I need to know this better or not? Okay. Now that's in practice. And in problem set 9, there is at least one problem with, maybe 2, where they didn't give you a coefficient of friction. And I picked those problems deliberately, so you had to go make an estimate. If you pick something different from the solution that I'm about to show you, that's not wrong, as long as it's not outside the reasonable range. I think the range in the book was given from 0.08, which is about what you need for self-locking, or 0.09, something like that, to 0.2, okay, in power screws with the surfaces they've got. So somewhere in that range is reasonable. 0.4 is not reasonable, okay? 0.25, that's fine, that's a possible worst case. You have to do it. On the exam, that's not fair game, okay? That's for in practice, so it's important to see that sort of stuff in the homework and for us to discuss it, because that's what's going to happen. In the exam, you'll be given what DC is or what F is, okay? These are specifics of the problem you're about to solve, or specifications for the problem you're about to solve, and they're given. So you don't have to do this sort of estimation. Okay? That's the brief answer to your question is no, you don't have to do this in the exam. It's not reasonable in the amount of time you've got. Okay. Any other questions on that? But that's roughly why I just picked DC and just took it as half of the outside diameter of the inside hemispherical cap. And that was an overestimate. This is problem set 9. And the first problem here is just a reworking of something that you already had in the previous problem set. I'll let you just go through and check it. The reason I put this problem on again is it's a good problem. This is sort of the core of designing a reduction gear set. You would have to actually pick the gears and pick the teeth, and they're given to you. And then once you've done that, the next thing you do is you go get the bearing forces, okay? And this sort of process here will get you the bearing forces. And then you pick a possible bearing, okay? And you start, pick what's the smallest bearing you can have, and anything above that you can have. And then you design the shaft using the stuff we've had for fatigue. And the shaft is very likely to have both bending and torsion in it, okay? And in which case that's one of the standard fatigue analysis you do. And then you go back and finalize your bearing. So there's really not a lot to this. I'll let you look this over. But just calculating the omegas. This question in the book asked for 100% efficiency or 95%. You get slightly different torques. So what happens here in a reduction gear set is the output torque has gone down significantly, but the output torque has gone up significantly. At 100% efficiency, it doesn't matter whether you use a driven pinion or not. Then there's these free body diagrams. These are all reposted, and they're in two planes. Okay, they're fairly simple. Okay. And then you combine to get the forces. So the next problem was this clamp here, and as I intimated last time, it doesn't have to be lifting a load. It could be just compressing stuff. And the C clamp, that's what it typically does, rather than lift a load. Their drawing is not completely consistent with the problem statement, but that's okay. And one of the things that's in the book that I want to tell you don't need to worry about is what they've done is quite correct. There was this thing called alpha N, and alpha N is a correct piece of geometry, but it's insignificantly different from just alpha, which is 14.5. So don't worry what alpha N is, okay? It's not examinable, okay? And you get the same answer with alpha. It's a little curious to me that that's certainly correct. It's a little bit academic though, to put in stuff like this. It's not going to make any difference. That's why I didn't bother teaching it. Okay. They also had here, they referred to section 10.31 and they made an estimate of the coefficient of friction of 0.15. That's not necessarily the correct number, okay? That's their number. It's not a stupid number at all. It's a decent number. If you pick 0.1, that's fine. If you put 0.2, that's fine, okay? The lead is given, on the other hand. That's what I put in. Okay. The same thing happens in the next problem. They have alpha N again, and you don't need to worry with it. Okay? It's
Dr. Sinclair.
Yes.
So in your notes, when we were first learning about this, you gave us that the pitch equals 1 over the number of teeth per inch of the screw.
Yes.
You also gave us that the pitch equals the major diameter minus the root diameter. Both of those expressions would give us different values for the pitch in problem 2 and 3. So
where do you have now? Where do you have DR?
DR, well, don't we have to? We're able to calculate DR, right, or find it from table 10.1.
You calculate DR using the pitch, so you use the same pitch.
Okay.
Okay, so there's no inconsistency. Okay, if you use DC or something like that as DR, then you get a funny answer. Yes, remember that's the diameter, the effective diameter of the column. Okay, which is big. Okay, but it's basically close to 2 inches. Okay, and
well, aren't we able to find DR from table 10.1 in the textbook?
Oh,
for Acme screws?
No. Yes. I wouldn't assume that the problem was consistent with that table unless it said it was. Okay. So, okay. No. That's a fair way to do it. Yes. Okay. What you've done is reasonable. You go and get standard threads from that table. That's fair. The people doing this problem didn't choose to do that. Okay.
The table 10.1 doesn't have Acme screws. Table 10.3 has the Acme screws.
It does it?
So
Okay,
for
well,
2 and 3, you'd have to use table 10.3.
yeah, okay. And so they may have done this problem in a way that's inconsistent with the table. Okay, from what you're telling me it is. So in the final exam, you'll be either told to use the table and given it, or given the table, and you'll need to use it, or you won't be, in which case you just use the formulas. Okay, and so P is D minus DR, and P is 1 upon N, where N is the number of threads per, the standard US number of threads per inch. Okay.
Okay, thank you.
Sure. Yes, I hadn't realized that, and this goes on for some length. It's double threaded. It's okay.
Did you say that we could neglect alpha n?
Yes,
Okay.
just use alpha. Just use alpha. We never covered alpha n. I'll tell you that what they've done about alpha n is correct, okay, but inconsequential. Okay. I haven't seen it matter, so I didn't bother teaching it. And you can go check on these work solutions. You'll get exactly the same answer if you just use alpha. Then 4, they're asking one of the things in 4. One of the things that happens in these problems, which I sort of stopped doing a bit, is that they'll calculate this inclination angle lambda. The formulas I gave you, we fed in what this lambda was into the formula, so you don't really have to calculate. But this is a typical value. It's less than 10 degrees, usually between 4 and 10 degrees, okay, if you did calculate it. But you don't have to. With the formulas I gave you for T versus W, there's no lambda in it. Not explicitly, implicitly, but not explicitly. So you don't, here they calculate the F required for the sort of square thread of it, for it to be self-locking is 0.08, and I think we got 0.09 for one of these. That's a sort of typical number. About 0.1 is what you need to do to make it self-locking for most of these power screws. And then the last thing here was some stresses. As I commented when in the lecture on Monday, the idea that the sigma A is
Move
negligible.
the paper down.
Sorry, thank you. That the sigma A is negligible compared to this is never sensible. But it's because the torque that goes into this is smaller because of the mechanical advantage. And so the two are comparable, and that's what's happening here. This is a bearing squared for the first thread and bending, okay? Then the last part of this question asks you the peak in terms of magnitude principal stress. Well, you get this large compressive stress. This is what I made an error in the first part, sigma A upon 2. Sigma A, that's the magnitude of sigma A. Or you can put plus sigma A like I had and put the minus sign in. This will be a significant stress when you combine these two. And it's bigger than either one of them at 58.5. But actually the biggest principal stress in this is sigma B. That's in a different plane, but it's bigger. And so that's the right answer here. Are there any questions about problem set 9? As I said, I'll post all this. I went through this reasonably quickly, and you should look it over and make sure that you understand what's going on. Okay? But are there any questions about this?
Can you go over part E of the last problem?
Part which?
E.
This part here? Yeah. Okay. I think
Okay.
let me see what it said. It said, ooh. Huh. A, B, C. A, B, C.
Is it a problem 6 or problem 5?
Problem 6.
Problem 6, yes. Yes. And also, I see, yes, my mistake. Okay. It didn't ask you for the maximum principal stress. I had a version of this.
Problem 5 did. I don't know if
No.
you're.
I'll have to check this out. I seem to have got my problems mixed up. Oh, it's problem, yes, this is problem 5. Okay. And I guess, yeah, this is problem 5. Sorry. Not problem 6. And yes, okay. Sorry, this is problem 5. And I see there's a problem 6 here, and I didn't put the solution in for problem 6. I must have stopped, right? So I'll post the solution to problem 6.
There was in our homework solution help that MDOT gave us. He gave us an equation for the bending stress.
Yes.
That was kind of different from yours. I couldn't find where that was in our notes.
Okay.
You gave
Well,
us, you gave us 2 points. You gave us that one.
yes, that's
And
right.
he used one where there was a 1 plus sine alpha squared on the bottom.
I'm not sure I know what you're talking about. The formulas I gave you were this, 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 and this. Those are the formulas. Right.
Okay, so for bending stresses, always go to, I think that's what, part 4 that you on your page,
Yes,
that equation right there.
that's the bending stress. In a power screw, we have typically 6 threads engaged. If you start to have fewer threads, then this number 2.4 would change. But for a power screw, this is the right number for bending. Okay. Yes. And so, yep.
That is specifically though for a square power screw, right? Because we calculated using the section modulus. If
Yeah,
we
this
have,
was all all the stresses here were done for square teeth.
I believe problem 6 had an Acme thread. And so what would be the section modulus for the Acme thread for calculating the bending moment? I think that's what his formula was using, but we were never given that in class.
Yes. Well, as a first estimate, you could just use the square. Okay. I'll have a look at that.
Okay.
And I'll post something with the solution this afternoon. Okay, so I forgot about problem set 6. So I guess my homework grade's going down. Okay. And it did ask for the maximum principal stress, and it's tempting to go for this big compressive stress, but actually this bending stress is the principal stress. It's in a different plane, so hence it's sigma 3, but it's actually the biggest stress. This is often the case. Bending stresses are nearly always the biggest stresses you've got. Okay. And I'm sorry I didn't do problem set 6, problem number 6. Okay. So let me.
Could you
Yep.
see what problem it is? Could you go to problem 3, part C, real quick?
Okay. Let me see if we can find it. Yes. So this part here.
Yes. Can you move it up just a little bit? It's
Yeah.
a little out of focus.
Okay. This is just this angle. Let me see. I don't have a book with me. Let's see. So it's like for square thread.
Part
do you
C is
ever-
the efficiency.
Yeah.
Oh no, it's an Acme thread. Okay. Yeah. Estimate the efficiency of jet when raising the load. But that's the part C you want, huh?
Yes.
Okay, sorry. So at some point I checked this. So
Can you slide your paper up about 6 inches?
sorry, yeah. Something.
About, yeah, we can't see any of the bottom.
So the work input is 2 pi t, and that was 16 apparently, 105 Newton meters. Work output derivative is the W, the weight, times the lead, how much it's moved. That turned out to be 40.8. I'm assuming they've got the details right. Then the efficiency is about 40%. So the work in over the work out, or the power in over the power out, same thing, as that's per unit time. So the work input is you revolve the screw 1 revolution, so the angle transverse is 2 pi, and you multiply by t. 2 pi is dimensionless, but t is Newton meters. That gives you Newton meters. Work output is how much you move against this force W, which you might be lifting it, but again, it can just be compressing something. So it's W times the lead. The lead is defined to be the amount you advance in 1 revolution. I guess this is a double thread, and so the pitch must have been 0.0051, and then 2 times that is the amount you move because it's double thread times the load, and so you get 40. Okay, and that if you take the quotient of these two, then you get this 46%. Is that okay? 40.6%.
Can you go to the page beneath and explain why they increased the friction coefficients?
Page which?
The page beneath that one, the yeah, just remove that one on top.
Okay.
And you see on number 4 for starting,
Yes.
increase the coefficient. Can you explain that?
Sure. This is not a bad rule of thumb. Okay. Now, let me clarify practice versus what you're going to have in the final. Final, you just take coefficient of friction. Okay. So right. Okay. But there's increases in friction from when things start to roll to when they're actually sliding. And so if you get the coefficient of friction by just finding the angle. Right, it's a bit thick. The angle at which something you won't see this, but I'm lifting this page here. And when you get it up high enough, it starts to slide. Okay, and if you lower it once it starts to slide, it will keep on sliding, meaning that the coefficient of friction has dropped a bit. Why does that happen? The predominant reason it happens, and it's not that reliable, not that consistent, is you get some humidity, okay? And the humidity, you have fluid, typically water, at where the solid attached to the other solid, and it has a little bit of tensile capability, and you have to break that bond to get it started. Once you broke it, it doesn't reform. Okay, there are possibly some other reasons, and it's possible too that when things sit for a while, that they move slightly, and the irregularities of the small surface irregularities conform more closely, and so you have more difficulty getting the thing started for that reason. Those are the two principal reasons. One of the things that this means, if you have very dry situation, sometimes the difference between the two is basically negligible. So this rule of adding 1/3 for starting friction is a rule of thumb. It's an approximation. Okay.
All right, thank you.
And that's what it is. But it's clearly quite approximate because the various sources for these things, I'm not sure that I've given you an exhaustive list by any means, but the principal sources I know of vary. One of them depends upon what are the minor surface features of the surface. The surface may look perfectly smooth to you, but at a small enough size scale, it'll have variations, and how well do they fit with one another? Okay? And if the frequency and amplitude of those variations are similar in the two, then you can have a significant increase in friction as it gradually moves and sort of fits meshes perfectly. That's one source. And the other thing is humidity. And you can see these differences if you measure starting frictions in a lab where the humidity is low, and the same two surfaces in a lab where the humidity is relatively high.
Gotcha. Can you bring back that other page? Because I noticed my T value is a little bit different.
Well,
So do we add, so that first T equals W times dm over 2 for 6?
yeah,
You add in for 6, go down.
Yep.
There. You add in that WFC.
Yes, that's right. Yeah.
That's right. Okay.
You add these whether you're loading or unloading, you add these, okay? It's always going to increase your torque.
All right. Thank you.
I think
Right.
that calculation for number 6 is wrong as well. Or number 7.
I doubt that because I would have checked it. But
A few of us are getting some different answers. I
What
don't
do
know
you-
if anyone else is.
what are you getting?
I'm getting 21.35.
Okay, well, let me take a note. I've got to do here. This is number. And problem. Okay, so I'll look at that.
And
see.
then part 8 is a little different as well. So I guess just
Okay.
check both.
Okay, I'll check both of them.
Thank you.
Usually I check these before I post them. So I'll be surprised, but I may not have. I don't usually post the solutions, the given solutions, unless I've checked them. Okay, anything else?
Yes, sir. For the efficiency, you gave us, we worked out an equation that was similar to loading up and the loading up and loading down equations, where it's a function of L, dm, F, L, like it's more than just the WL over 2 times pi times T. You know what I'm talking about?
Yeah, I gave you a formula, but if you actually calculated the torques already, you don't have to use that formula. It'll be consistent with it.
Right, but if you do use the formulas,
Yeah.
would you include the WFC DC over 2 terms in that
Yes.
equation?
Yes, if that you're losing that, and so that's going to change your efficiency. Yes.
Okay.
Okay.
And I misspoke. When I said part 8, I meant part 6, not part 8. For getting a different answer.
Oh, okay. Part 6. Okay.
Yes.
Okay, I'll check part 6.
No, 6 and 7, not 7 and 8.
Okay.
Sorry.
Okay, that's all right. I'll check them. Any other questions here? This is fairly detailed stuff, and you need to take some time going over it. Okay. All right. Well, let me make some comments about the final. The final is next Monday. Okay. And as I told you, it's 4 questions. One and 2 are 10 parts each. And they will walk the waterfront. They will be spread out throughout the entire class. Okay. Now, there's enough stuff covered in this class that not everything we've done will be there, but a lot of it will be. Okay. And these will be these 1-point questions where you want to preferably write down the formula you're using and implement it correctly. That's basically what you have to do for most of these. Yeah. If you write down the formula correctly and implement it incorrectly, then you can get half credit. Okay. That's one of the reasons why I've given you a generous amount of formula sheets. Okay. I don't think you really need, you've got 3 two-sided formula sheets. I did have an experience 2019 where some students felt like they could use a little bit more than 3 one-sided. I'm not sure any of them needed 6 one-sided. But anyway, so that's the reason for increasing it. Okay. Make sure you've got any formulas you need. Okay. As I've said in the past, this is an opportunity for really screwing up your time here. You've got 2 hours. Okay. Unless you've got extra time. And then these things are worth half an hour each. If you start spending 5 or 10 minutes on a single part, that's only going to be worth 1 point. Don't do that. What I've suggested you do is when you look at these, just do the ones that are easy, then get to questions 3 and 4, which will be on problem sets 7, 8, and 9. Okay, that's what 3 and 4 will be on. And work those, and then go back and work whatever parts of these things here that it wasn't too obvious to you. Now, one of the things this requires is you have an appreciation for what you know well, what you know sort of, and what you don't know. Well, that's an important appreciation to have as an engineer. Okay. But, and I would encourage you to check your work, because you make errors in calculations, you're going to lose points. Okay. I will post the solutions to the practice test. Practice final.
Are parts 1 and 2 from all the problem sets, or just the 1 through 6?
Oh no, they're from all. Okay.
Okay, perfect.
Yeah, that's a fair question. No. You could have some of the last problem sets in this. Yes. So this walks the waterfront. This is the entire course. Okay.
Okay,
In some
thank
sense-
you.
And so that's a very fair question. So in some sense, problem sets, the latter problem sets use the earlier stuff anyway, even if it's only implicitly. Okay. So yes, so these are entire course. I will post this on Saturday morning, and I will have office hours from 3:30 to 5:30 Saturday. Okay. I don't have office hours on Sunday. If you've got questions between now and Saturday, you can email them to me. I may get a chance to respond before the office hours. Okay. But maybe not, but I'll certainly try to respond during the office hours. When you email me, it's a good idea to include a phone number so I can call you. Okay. It's usually faster to talk on the phone than for me to email you with my typing or non-existent typing skill. Okay. But and we can discuss the thing. But if push comes to shove, I can send you an email back. Okay. And that's about all I have to say about the final, but I'll take your questions with the understanding that this is the only opportunity to ask questions about the final. If you email me a question about the final, then no, I'm not going to respond at this point. Okay. Well, let me reiterate something else I've already said. You know, there's in design, you make estimates and stuff like that. In this final, you will not have to estimate an F or something like that. You will be given Fs, or you'll be given a DC or something like that. You won't have to estimate it. Okay. It's partly because finals are a little artificial in that you're constrained in access to information that we'd have to make these estimates. So it's not altogether reasonable to have you make an estimate. Once you've been out in practice for a while and you know certain areas, you'll be able to make estimates just from what you know without looking stuff up. But that's after you've been out in practice for a while. So you'll be given the specifics that you need to solve problems. You won't be given any formulas. If you need a chart or something like that, that you'll be given. If you need a table, that you'll be given. Okay. All right. Any questions about the final?
I have a question, Dr. Sinclair.
Yep.
Is MD going to send out the Zoom links like he did for the first 2 tests? On which
Sorry.
is MD going to send out the Zoom link meeting?
Yes, it'll be set up the same way as the first 2 tests were. Okay.
Okay, great. Thanks.
So you need to find which group you're in, and that's what you join. There's a couple of you on both tests who didn't bother putting their name on the test. That's very modest, but you know you're probably going to score more if you actually. I doubt anybody scored 0, so probably a good idea to put your name on the test. So that's the setup will be essentially the same as for the first 2 tests, except you'll have an extra half an hour, but you've got an extra problem. Okay. I think that actually makes for a better exam, having a little more time. but you've got to watch your time. There's more than one student who did a good job of the first question in, say, even test 1 or test 2, but then ran out of time to do the other questions. Okay, so what that probably means is they didn't quite know the material for question 1 as well as they thought they did, and it took them a bit longer, but they sort of knew it, but then they ran out of time for the other stuff, and that didn't help their score. So you don't want to do that. Any other questions? You sure? All right. Well,
Dr. Sinclair, I have a question.
sure.
I know a lot of us have been going to this class. Well, I mean, we all have been going to this class virtually over the past semester. And in a normal scenario, we'd be seeing your face every day. And I know I speak for myself and probably most of the rest of us when I say, I mean, before you kind of break one last time, I wouldn't mind seeing your face because, I mean, I'm not sure if I'll ever see you again while I'm here. So I'd appreciate if we could see your face one last time.
Well, you've got the wrong guy. I'm not quite sure how I put my face up on this thing. Okay, maybe if Mohammed shows up, he can. But you know, you're not missing anything. Let me tell you. You know, no. The kindest words to describe my face would be character, maybe. Not necessarily good character. I had my nose broken 3 times. I don't quite know why. Once was in boxing with the small clubs. Okay, I walked straight into a punch in the first round. That wasn't great. But so yeah, I don't know quite how to put me up on this thing. So sorry about that. But, all right. Well, I don't wish you. Well, let me share a couple of things. First of all, I don't wish you luck on the final. I wish you justice. Okay, we will grade this very carefully, and I would hope that we'll have the grades by Wednesday. And we'll send out an email to this if we do at about 3:30. And it'll be in my office or in a room in Patrick Taylor Hall, and you can come and look at your files, okay, and check. We will check the addition, but that's the most likely mistake. It's also possible occasionally that you've solved something in a different way and we missed it. But other than that, it's very unlikely there'll be changes. But there's a department rule that you can't take that final away. We keep that final and we're going to use it for ABIT, amongst other things. Okay. So, but you're welcome to look at it and make sure it's okay. Then I'll probably post grades on Thursday if we get it graded by Wednesday. But I'll let you know on that. Okay. All right. Well, good luck in your careers. Okay. Have a good day.
Dr. Sinclair.
Okay.
Thank you for a good semester.
Oh, thank you.
Dr. Sinclair, I just got one quick question about my grade got changed for the last test, but it has been changed on Moodle.
Yes, I've got a meeting with Mohammed right after this class to make him fix that. He should have fixed it about 2 weeks ago. Okay. All right. I have any of the changes I've got recorded on my master list, so they haven't gone away. Okay.
Okay, that's what I was just making sure. Thank you.
Yeah. No, we'll get that fixed. Okay. And in some sense, if it never was fixed, my master list is not going to be used to calculate the grade. So even then, but I appreciate that you want to look on Moodle and see a correct score. Yes, I understand that. Okay, have a good day.